Imagine you possess a weapon so advanced, it renders every enemy aircraft obsolete. A fighter born of fire and speed, appearing in the skies over a collapsing empire, flying 100 miles per hour faster than the fastest propeller-driven plane the Allies can field. It should have been a war winner. It should have been the silver bullet that reversed the tide of an unwinnable conflict. But this miracle weapon, the Messerschmitt Me 262, harbored a dark and fatal secret. A flaw measured not in months, weeks, or even days, but in hours. What if your ultimate weapon was designed with a self-destruct timer, one that began counting down the moment it was first ignited? What if its heart was engineered to last at best for 10 short hours of flight? This is the story of that engine. A story of genius and desperation. Of a technical nightmare that crippled Germany's jet-powered dream before it could truly take flight. This is the story of the 10-hour engine. The dream of jet propulsion was not exclusively German. Across the Channel in Britain, a brilliant RAF officer named Frank Whittle was wrestling with his own centrifugal flow jet designs. But within the Third Reich the pursuit had a unique, frantic urgency. As early as 1936, a young physicist at Göttingen University, Hans von Ohain, had secured funding from the aircraft manufacturer Ernst Heinkel. Von Ohain was a visionary, a purist. He chased thermodynamic perfection, designing elegant complex engines that, while groundbreaking, were closer to laboratory instruments than rugged, mass-producible weapons of war. His Heinkel HS-3 engine would power the world's first true jet aircraft, the Heinkel He-178. In August of 1939, a week before the invasion of Poland, it was a stunning achievement, yet the Heinkel engines remained finicky, underpowered and far from ready for combat. The German Air Ministry, the Reichsluftfahrtministerium or RLM, was intrigued but not yet convinced. They needed power, and they needed it in numbers. The RLM therefore initiated a parallel development program. They hedged their bets, approaching established engine manufacturers like Junkers Motorenwerk, or Jumo, and BMW. The task at Junkers fell to a man who was in many ways the antithesis of Hans von Ohain. His name was Dr. Anselm Franz. Franz was not a physicist chasing theoretical ideals. He was a pragmatic, experienced engineer, a specialist in supercharges and turbocharges. He understood the brutal realities of mass production, of battlefield maintenance and of supply chains. He knew that an engine which could not be built by the thousands with the materials on hand was nothing more than an intellectual curiosity. This fundamental difference in philosophy between Franz the engineer and von Ohain the physicist would define the fate of Germany's jet program. Franz and his team at Junkers immediately departed from the path taken by both Whittle and von Ohain. Instead of a centrifugal flow compressor, which takes in air and flings it outwards like a spinning disc, Franz chose a far more complex but potentially more rewarding design, the axial-flow compressor. Imagine a series of miniature spinning fans, all stacked one behind the other on a single shaft. Each fan or compressor stage takes the air from the previous one, squeezing it a little bit more, increasing its pressure and temperature before forcing it into the combustion chambers. The advantages were clear. An axial flow engine could be made with a much smaller diameter, creating less drag and making it perfect for a sleek high-speed fighter. It was also, in theory, more efficient and capable of generating significantly more thrust. But the challenges were monumental. The mathematics were a nightmare. The aerodynamic profile of each tiny blade in each of the multiple stages had to be perfect. A mistake in one stage would be magnified catastrophically in the next, causing the airflow to stall and the engine to violently choke on itself. A phenomenon known as a compressor surge. The tolerances were measured in fractions of a millimeter. It was a design of incredible complexity, a delicate spinning symphony that required a level of manufacturing precision that was, even in peacetime, staggeringly difficult. And Germany in 1940 was not at peace. It was a nation gearing up for total war, a war that would soon place incredible strain on its industrial resources. The first prototype of Franz's engine, designated the Jumo 004A, ran in the spring of 1942. It was a monster. Weighing over 2,200 pounds, it was heavy, complex, and built using the finest materials Germany could provide. The compressor blades, the combustion chambers, and most critically, the turbine blades at the hot end of the engine, were all made from alloys rich in nickel, cobalt, and molybdenum. These were the strategic materials, the exotic metals with incredibly high melting points, capable of withstanding the hellish environment inside a jet engine where temperatures could exceed 800 degrees Celsius. The Jumo 004A worked. It produced the required thrust, A pair of these early engines were fitted to a prototype Me 262 airframe, and on July 18, 1942, test pilot Fritz Wendell opened the throttles and lifted off the runway at Lytham. For the first time, the iconic shark-like form of the 262 flew purely on jet power. It was a triumph, but it was a hollow victory. Anselm Franz and the officials at the RLM knew the terrible truth. The Jumo 004A, as it was, could never be a wartime engine. Germany simply did not have the nickel, the cobalt, or the molybdenum to build it in the required numbers. The nation's conquests had secured iron and coal, but the rare metals needed for high-temperature metallurgy were controlled by its enemies. The supply was dwindling with every passing month. The RLM issued a stark, seemingly impossible directive to Franz: redesign the engine, redesign it to be built without these critical strategic materials, and do it yesterday. The entire Me 262 program, the hope of Germany's air defense, now rested on Franz's ability to solve an unsolvable problem in materials science. He was being asked to build an engine capable of containing a furnace, using materials barely better than steel. This was the devil's bargain. This is where the legend of the 10-hour engine was born. To meet the RLM's demand, Franz and his team initiated a radical, desperate redesign that led to the production model, the Jumo 004B. Every component was scrutinized. The goal was no longer perfection or even longevity, it was producibility. The weight was slashed by over 500 pounds. The complex starter system was simplified, but the most critical changes were made at the engine's hot, violent heart. The nickel and cobalt-rich alloys were gone. They were replaced by what were essentially exotic high-chromium steels. For the critical red-hot turbine blades, Junkers developed two solutions, both born of desperation. The first was an alloy called tinida, made mostly of iron, with about 30% nickel and 15% chromium, a significant reduction in the precious nickel content. The second, even more desperate solution, was to use blades made from chromadur, a simple chrome steel alloy that was essentially a type of high-quality stainless steel. These materials were nowhere near as heat-resistant as their predecessors. Under the immense temperatures and centrifugal forces inside the engine spinning at over 8,700 revolutions per minute, these steel blades would begin to stretch. This phenomenon, known as creep, would cause the blades to elongate slowly at first, then more rapidly, until their tips would eventually make contact with the engine casing, resulting in a catastrophic explosive failure. Franz and his engineers knew this. They couldn't change the laws of metallurgy, so they did the only thing they could. They found a way to cool the blades. The solution was as ingenious as it was desperate. They designed the new turbine blades to be hollow. A small amount of bleed air was siphoned off from the engine's own compressor, ducted through the turbine shaft and forced up through the hollow core of each of the 61 individual turbine blades. This constant flow of relatively cool air acted as an internal refrigerant, drawing just enough heat away from the metal to keep it from melting or stretching past its limit. For a time, it was an incredible feat of engineering. The blades were formed from sheet metal, folded over and welded shut, a manufacturing process that was far easier than casting solid blades from exotic alloys. But it was a patch, a band-aid on a mortal wound. It bought the engine a few hours of life, nothing more. The operational life of a Jumo 004B turbine blade was rated at a terrifyingly brief 10 to 25 hours. After that, creep would inevitably set in. Maintenance crews were instructed to inspect the engines with a horrifying regularity. They would sometimes use a simple gauge to check the length of the blades. If they had stretched by more than a few millimeters, the entire engine was condemned, removed, and sent back to a factory for a complete rebuild. For the pilots, this meant every flight was a gamble. Every takeoff was a roll of the dice against the fundamental laws of physics and material science. The engine's fragility dictated every aspect of its operation. A pilot transitioning from a piston-engine fighter like a Bf-109 to the Me 262 had to unlearn everything he knew. In a propeller plane, the throttle was a direct command. You pushed it forward, you got power, you pulled it back, you slowed down. To do so in a Me 262 was to court instant death. The throttle on the Jumo 004 was more of a polite suggestion. Because of the engine's delicate thermal balance, throttle movements had to be impossibly slow and gentle. Pushing the throttle forward too quickly would inject a rush of fuel into the combustion chambers. The fuel would ignite, but the turbine wasn't yet spinning fast enough to move the massive volume of hot gas. The temperature would spike uncontrollably, far beyond the melting point of the cheap chromadur turbine blades. The result was a flameout, or, far worse, a burner can blow through, where the turbine would overheat, disintegrate and send a shower of white-hot shrapnel tearing through the rear of the engine, the wing, and the fuselage. Slowing down was just as perilous. Pulling the throttle back too quickly could extinguish the flame in the combustion chambers. A flameout, relighting a Jumo 004 in midair, was a complex, heart-stopping procedure that rarely worked. With 2 dead engines, the sleek futuristic fighter jet became a 15,000-pound glider with the aerodynamic properties of a brick. Pilots learned to fly the engine, not the airplane. Their eyes were glued to the exhaust gas temperature gauge. Reading above 600 degrees Celsius was the danger zone. Any sustained period above that, and you were living on borrowed seconds. This slow throttle response also made the Me 262 a clumsy dogfighter. It was a creature of speed, a one-pass interceptor. It could not turn and burn with the nimble P-51 Mustangs and Spitfires. Its only defense was its astonishing velocity. Even starting the engine was a uniquely German over-engineered affair. It didn't have an electric starter. Instead, nestled in the nose cone of each engine was a tiny 2-stroke gasoline engine called the Riedelanlasser. To start the jet, the ground crew would first have to start this tiny engine, which they did by pulling a T-handle in the wheel well, like starting a lawnmower. The little Riedel engine would shriek to life, its high-pitched scream slowly turning into the deeper rising whine of the main turbine as it spooled up. Only when the main engine reached a specific RPM could the pilot introduce fuel and ignition. It was a complex, multi-stage process, a world away from the simple prime, pump, engage of a Merlin or an Allison engine. The logistical implications of this 10-hour lifespan were staggering. The Jumo 004B was not designed to be repaired in the field. It was designed to be replaced. The engine was mounted to the wing with just 3 bolts and had quick disconnect fuel and electrical lines. A trained crew could, in theory, swap out a dead engine for a new or factory rebuilt one in as little as 3 hours. Airfields became vast open-air workshops littered with engine cowlings, cranes and piles of time-expired engines awaiting shipment back to the factories. It was a logistical nightmare superimposed on a material science crisis. Germany was producing a disposable jet engine, and the demand for replacements far outstripped the heavily bombed industry's ability to supply them. For every Me 262 in the air, there were several more on the ground, waiting for a new heart transplant. When these fragile, magnificent machines did get into the air, they were a terrifying sight for Allied bomber crews. In the autumn of 1944, pilots of the 8th Air Force began reporting encounters with aircraft that moved with an unnatural speed, leaving their P-51 Mustang escorts struggling to keep up. The Me-262s, flown by elite units like Jagdgeschwader 7, would approach the bomber formations from high astern, their speed differential so great, over 150 miles per hour, that the .50 caliber gunners in the B-17s had almost no time to track them. The 262 pilots had their own problems. This high speed made aiming difficult. They were on top of the bombers in a heartbeat, with only a second or two to fire. Their primary armament was 4 30mm Mk108 cannons in the nose. These were low-velocity mine-shell firing weapons that could tear a B-17 apart with just a few hits. Later they were equipped with racks of R-4M air-to-air rockets, which could be fired in a devastating salvo from outside the range of the bomber's defensive fire. In the hands of an experienced ace like Walter Novotny or Adolf Galland, the Me-262 was a deadly bomber killer. But for every successful interception there were stories of disaster, engines flaming out on takeoff, turbines disintegrating during the high-G climb to altitude, pilots being forced to bail out of perfectly intact airframes because one or both of their engines had simply given up. The Me-262 pilot's greatest enemy was often not the hundreds of Allied fighters in the sky, but the 2 ticking time bombs bolted to his own wings. The strategic mismanagement of the program only compounded the technical flaws. Hitler, obsessed with vengeance weapons and offensive capabilities, saw the sleek interceptor and famously demanded it be turned into a blitz bomber. He ordered that the aircraft be fitted with bomb racks to carry a small payload, a role for which its high speed and poor low-altitude handling made it completely unsuitable. This decision, born of strategic delusion, caused months of delays, wasted precious production resources, and infuriated the Luftwaffe's senior leadership, including General of Fighters Adolf Galland, who saw the 262 as their only real hope of stopping the Allied bomber offensive. By the time the Blitzbomber order was rescinded, and the 262 was finally unleashed in its intended role as a pure fighter, it was late 1944. The war was already lost. The skies over Germany were owned by the Allies, and the fuel, pilots and engines needed to make a difference were simply gone. In the end, the Jumo 004 was both a staggering success and a catastrophic failure. It was the first axial-flow jet engine to enter mass production, with nearly 6,000 units built. It powered the first operational jet fighter in history, and yet its inherent engineered unreliability made it a logistical black hole that consumed resources the Reich could not spare. The 10-hour engine was a perfect microcosm of the entire late-war German arms industry. Technologically brilliant, breathtakingly advanced, and fatally flawed by a foundation of desperation and scarcity, it was a weapon for a war that Germany could have won in 1941, being built by an industry that was collapsing in 1945. The war ended. The Me-262s were captured on their airfields, some pristine, some half disassembled, all silent. But the story of the Jumo 004 was far from over. Allied intelligence teams, particularly the Americans and the Soviets, depended upon the Junkers factories and design bureaus. They didn't just want the engines. They wanted the blueprints, the test data, the tooling, and most importantly, the engineers. Dr. Anselm Franz and many of his key personnel were taken to the United States as part of Operation Paperclip. The Soviets captured the Junkers factory at Dessau and carted the entire production line along with its German workers back to the Soviet Union. The legacy of the 10-hour engine was immediate and profound. The brutal, hard-won lessons learned by Franz's team about compressor aerodynamics, thermal management, and hollow blade construction became the foundational knowledge of the entire jet age. In the United States, captured Jumo 04s were meticulously reverse-engineered. This work directly led to America's first axial-flow jet engine, the General Electric J-35, which would power the F-84 Thunderjet and the F-89 Scorpion. In the Soviet Union, the captured Jumo 004 was simply copied, designated the Klimov Rod-10, and rushed into production to power the early Soviet jet fighters like the Yak-15 and MiG-9. Even the British, who had pioneered their own successful centrifugal flow engines, studied the German axial flow designs with intense interest. The bloodline is undeniable. The engines that would power the next generation of iconic fighters, the F-86, Sabre, and the MiG-15, which would duel in the skies over Korea, were direct descendants of the Jumo 004. They were built with the proper strategic materials that Germany lacked, free from the desperate compromises that had condemned their ancestor to such a short, violent life. The technical nightmare of the 10-hour engine had taught the world's engineers invaluable lessons, paid for in the desperation of a dying regime. The flawed, self-devouring heart of Germany's first jet became the blueprint for the very engines that would define the Cold War and carry aviation into the supersonic era. It was a weapon that failed to save its creators, but in its spectacular, intricate failure, it succeeded in changing the world. And that concludes this story about the 10-hour engine, the technical nightmare of Germany's first jet. If you want to learn more about World War II, subscribe, like, and share. Also, leave your anecdotes and ideas in the comments section.